Hi, everyone. Good afternoon. Thank you for joining today's presentation. I'm going to let people join in from the waiting room before I announce today's presentation here. I think we're starting to see people join. So today's presenter is Rob Haley, and the presentation is Introduction to Thermal Bridging Solutions for the Building Envelope. A few things to note about today's presentation here. First one, there will be a webinar poll about 3/4 of the way through the presentation. Feel free to fill out any requests, whether it be including project details, requesting price quotes, product literature, technical information, samples, or all of the above here. The Q&A is open. You are welcome to submit questions through there or chat them as well, and we will get to them at the end of today's presentation. And the last thing I want to show you guys is where to find thermal bridging solutions on Acelab here. So I'll make sure to include this link in the chat. Okay. Oh, I might need you to stop sharing your screen, Rob, if you don't mind, real quick.
Sure.
Thank you. Okay. So this is thermal bridging's page on Acelab. You'll be able to see a little description about what they do and the experience here, as well as a direct way to contact Robert. So if I scroll down here, you've got some really great products here, including their TBM1, which here gives you a lot of really great information about the product and some more details as well about the energy codes and moisture control. So feel free to go check out their brand page. I'll link it in the chat as well. And I think that is everything before we can go ahead and get going.
Okay, so I should share now.
You can share now. Thank
I
you.
can share now. Okay. How's that?
That looks great. All good to go.
Perfect. All right, is everybody in? Should we start?
Yeah, let's get going. People can join as they come.
Okay. Good afternoon, everyone. My name's Rob Haley. I am a mechanical engineer by degree. Spent most of my professional life at a company called Fabrica, where I was the engineering manager towards the end of my career there. At Fabrica, I was responsible for the engineering and the marketing. And so the way I got into thermal bridging was that I was in Europe back in 2011 and saw thermal breaks being used per energy code. And I thought, Europeans did it again. They're 15, 20 years ahead of us, right? So came back, developed a material at Fabrica for bolted steel connections, which they still use today. And then Fabrica went from private to public, so I left and started a company with a friend of mine called Armadillo, which turned into Armatherm, where I did all the engineering and R&D and thermal modeling. In 2019, we parted ways, and I started Thermal Bridging Solutions. So the moral of the story is that I've been involved with thermal bridging and thermodynamics and hydrothermal analysis, so heat moisture control, since 2011. Right, so that's where I am today. That's the title of the course, and we'll get started. The learning objectives. You may have already in the past 10 years or so taken another course about thermal bridging. This one I hope is a little different for you. I add a few things, a few topics that I feel are important for design professionals, building enclosure specialists, architects to know about thermal breaks and thermal bridging that no one, I think, talks about, but I would like you to know. So we're going to talk about where it happens in the building enclosure. We're going to talk about how it does affect, our value. We will talk about how thermal break materials and solutions can help reduce heat loss through the building envelope, and how they can also perform a second function of keeping the surface temperatures of materials within our wall and roof assemblies above the dew point. Lastly, we will look at how the solutions for thermal bridging can or might not change the R or U value of a wall assembly. Okay, so we'll start with where it happens in the building enclosure. And where it can happen is, the roof is part of the building enclosure. So it can happen at parapets. It can happen at equipment screen posts and kickers. It can happen at roof edges. It can happen at roof anchors. Basically anywhere we have a structural connection that penetrates through the thermal layer, right? And draws the heat out. So the roof is one place. If you design metal buildings or have used metal buildings before, um, when they attach the metal panels to the roof and the walls, they compress the blanket insulation up against the purlins, and that also creates a thermal bridge. One that most people are familiar with is the canopy or the balcony connection. Basically, we have steel or aluminum or even concrete, again, being attached back to the main structure, a load-bearing element that passes through the insulation in our walls and our roofs. Cladding attachments is another one people are fairly familiar with. Clips, girts, rail systems, anything again that is being secured back to those steel studs and is highly conductive is going to create a thermal bridge in the wall, right? That includes relief angles, for example, for masonry veneer. One that has been overlooked, but is certainly a big factor, is fenestration. And I'm not talking about the windows and the doors and the curtain walls themselves. Here, I'm basically talking about their location in the RO, in the rough opening, and where in a brick veneer wall, for example, lintels, you can see in that upper image, you can see the lintels are all very warm and cozy and conducting heat right through the brick veneer of that building. You can also see the horizontal lines. Those are the shelf angles conducting heat through the building. And in the lower photo image, rather, just all around the window, we're getting heat loss coming through the wall. Now, the let's call it the fenestration industry, the glazing industry, is these days they're all doing a fantastic job, not only lowering the U value of their uh, field of glass in the windows and the walls, but they're also doing a better job with the frames of the windows, meaning that if you've ever stayed in a hotel, for example, and you walk near the window and it's an aluminum framed window, you immediately, in the wintertime anyway, you start to feel a little cooler. That's because the aluminum is drawing the heat out of the room right to the outside. And in the morning, after you've run the heat all night, you might notice that the inside surface of the window has condensation. And that is because the frame of the window has now cooled down to the point where it's below the dew point in the room. And then what happens is that condensation goes into the sill and into the wall and into the gypboard and creates mold, and it's a fun time. So what many manufacturers have done is they've taken the window frame and they've split it in half so that we have a warm side and a cold side. And that way, that prevents that condensation from happening. But what can still happen is where you place that window frame in the opening of the wall, and you attach it back to the steel studs or the cold form steel studs, you can still draw heat from inside the room to the frame and then out into the stud and around the thermal break in the frame, right? I call that flanking. Other people call it flanking. And so that's where you get that orange, all the way around the frame showing up because the heat is still finding a way to go around the window and out of the building, right? And so that's another area where thermal bridging occurs. The foundation is also part of the building enclosure. And so wall to foundation transitions and floor slab intersections are another location where heat can escape. Talked a little bit about curtain walls just then, but curtain walls, where they get attached, the pressure plates and the mullions and so forth in the ground or to the structure, these are all typically also made of aluminum, highly conductive. And that's another location where heat can be drawn out of the building. So why does it happen? Well, it happens because the materials that we use in commercial building construction, aluminum, steel, concrete, even timber to some extent, they have very low thermal resistances and very high thermal conductivities, right? Here's another way to look at that. If we take a look at the top chart, these are the thermal conductivity properties of these materials. And then in the chart below, those are the R values, right? So R value is the thermal resistance, right? How much heat a material will resist. And you can see how low those numbers are, right? So Bad insulation, for example, or mineral wool insulation or polyiso insulation have much, much, much higher R values, of course, but they don't have the strength. Okay. And so that's the trade-off. I guess the stronger your material is, the more conductive it is. So that's why it happens. Um, and so why do we want to address thermal bridging in the first place? 10 years ago, I maybe could find two articles on thermal bridging here in America. It certainly wasn't addressed in energy code until probably 10 or 12 years ago, which we'll talk about in a second. It is being addressed now, thankfully, because it's been recognized to be a major contributor along with air leakage in energy loss and heat loss in a building. We, for years, underestimated how much heat, these thermal bridging anomalies actually took out of our buildings. It's no wonder that commercial buildings consume such large amounts of energy. And over the past 10 or 12 years or so, as thermal modeling became more popular, as testing of wall assemblies became more popular, we confirmed that you can actually reduce a wall's R value by more than 50% very easily with steel Z-girts or with steel beams, and we'll see that in a second. And so it's important because if you're doing whole building energy modeling, you want to have an accurate U value for your wall. If you're not familiar with U value is the reciprocal of the R value. Okay. So the R value is thermal resistance, how much heat we can resist. The U value is, let's say, a characteristic of a wall or roof assembly that tells us how much heat that assembly is capable of transmitting, okay, of conducting. And so that's important, right? Because if we're doing a ComCheck analysis or an energy plus analysis on a whole building to see how much energy it's going to consume or to validate if we comply with energy code, we should be using accurate numbers in there, right? And so that's why this is important. And lastly, I'd like to say building to code doesn't mean you're building energy efficient. A lot of prescriptive code lets you or allows you to build the best worst case scenario, right? So that's why it's important to address, just like air leakage is important to address. Okay. I hope most folks are familiar with this. This is the climate zone map of our country. I'm not sure if it's the most recent edition. I think it is. And so our country is divided up into these climate zones, and each climate zone has its own requirements for U values and R values of walls and roofs. To make it a little more interesting, every state chooses which version of a model energy code they want to adopt and enforce. So just because all the different states in climate zone 5 are in climate zone 5 doesn't mean they're all using, let's say, for example, the IEC C 2021. Some could be using 18, some could be, so where you design, where you reside, where you build, there's a lot of variables there. This is what let's say, typical U value chart looks like. This one's for climate zone 5. I use that because that's where I am, but it's just an example. Okay. And so in this chart, you can see that if we're building with cold formed steel studs, metal steel framed right here where it's highlighted, ASHRAE would like us to use R13 in the cavity and R10 as continuous insulation, right? And the thing about these numbers is that if you go further into table A3.3, which I show at the bottom in red there, we acknowledged years ago that the steel studs create thermal bridges, and that they derate or reduce the nominal R value of that batt insulation in the cavity. So we're starting at R13 because we recognize that, for example, if your studs are 24 inches on center, you're really only getting an effective R value of R7 from that 13. And if your studs are 16 on center, you're really only getting an effective R6, right? So you're losing half, let's say, half of your R value just from the studs, okay? And so what R13 plus R10 doesn't mean is it doesn't mean R23, okay? It means either R17.2 or R16 as an effective R value, okay? And that assumes further that the R10, the continuous insulation on the outside of our wall, is not derated, okay? So there's a couple takeaways from that. Here in Massachusetts, for example, we revert to the IECC 2021, And in our energy code, we're not allowed to use the R value method. We must use the U factor method, which is a different table. And in that table, it tells us that we need a U value of 0.055, which translates to an R value of 18.2. Okay. And the reason that mass does that is because of what's down below in the red. You can't say, hey, R13 plus 10 CI, if you don't know what the stud spacing is, you're going to get two different answers, right? So it's not as accurate as saying this is the U value you have to meet of the assembly. How you get there is up to you, but you have to have an effective R value of 18 point. So that's how that works. So here's a little picture of what we just talked about, right? We have cavity insulation. It gets derated due to the studs. We have, quote, CI, or continuous insulation in green, which will now also be derated by the cladding attachment system. So how do we characterize thermal bridging? One way is thermal transmittance. Transmittance is a fancy word for heat flow. This has been being done again in Europe for years. There's a firm in Canada called Morrison Hershfield, which is now Stantec, who did a lot of this thermal transmittance modeling, three-dimensional heat flow modeling of wall and roof assemblies. And they actually have, if you're not familiar with it, they actually have a great resource online. It's called the Thermal Bridging Building Envelope Guide. And there's hundreds and hundreds of walls and roofs, interface and transition details. And really what it is, we're trying to quantify the amount of heat, obviously, that is being transmitted through the wall assembly or the roof assembly in the form of a transmittance, right? And so what we have are basically three types. We have clear field, which is just our opaque or clear field wall and roof. And then to that, we can add a linear transmittance, which might be something like a shelf angle or a parapet or a wall to foundation transition where there's a linear characteristic. And then there's point transmittances, which are just single points like a balcony connection. And so if we add them all up, we get the effective heat flow through the wall assembly. So what we're after is to characterize this transmittance. So let's look at a few examples. Excuse me one second. It's not beer, I promise. It's Waterloo, still water. So here's a classic cavity wall, right? No stud insulation, chipboard, exterior insulation, and steel Z-girts. This is an example of a clear field application. If we do a thermal model of this wall, we get the results that are up here in the chart. And what I did, we have a range here, if you can see my mouse. We did a range here of exterior R values for the insulation. And then the next column here, this is the nominal R value that we expect to get out of this wall. And so you can see that it's a little higher than the insulation because there is some resistance with air films and with the dense glass or the chipboard on the outside. And then the third column is what we actually get. That's our effective R value due to the thermal bridging from the steel Z-girts, right? And so this is where we start to see, in this case, we're seeing a 39 to 49% decrease in that nominal R value of our CI, right? Just due to the girts. And for many years, say 10 years ago, the thought process for a lot of people was, the flange on a Z-girt's only 1.5 inches wide, 2 inches wide. That's not a lot. That's not a lot of surface area. How much heat could possibly come out of the wall due to that? And the answer is that in this example, the girts are only 8% of the wall area, but they're responsible for 40% of the heat flow out of that wall. And so you can't use area weighted averaging, let's say, for example, as a technique. You cannot also assume that heat flows in parallel, nice, neat paths only through these conductive elements because heat flows in 3 dimensions, right? And so that's why we get such a dramatic or significant decrease in R value just from this example here. This is what the model results look like. You can see that Z-girt is starting to cool down, heat up a little bit as it draws the heat through the wall. In a perfect scenario, it would be the dark blue color, right? But it's more in between because it's drawing the heat through the wall. Now, building science in recent years would suggest that we are better off building our wall. We should put all of our insulation on the outside and nothing in the cavity. And the reason for that if we have all our insulation on the outside, then we've done the absolute best job that we can at keeping that critical plane or surface of that exterior jip board warm, right? That's our AWB. That's our drainage plane, right? We don't want that material surface to drop below the dew point at any point in time. Because if it does, and if the materials behind it do, then we have a potential condensation risk, especially in colder climates at certain times of the year. And if we have condensation in our wall assembly and it occurs where we can't get at it, where we can't see it, where we can't manage it, then we start again to create problems, rust, deterioration, mold, rot, things like that. So that's why it's best to put it all on the outside. And you can see in the red oval now that I've placed there, if we didn't have the thermal bridging to contend with, if we had true CI, then we've got all these wonderful R values that can meet that can comply with all the different climate zones, all the way up to 8. But because we have the bridging, we now have a problem. How do we, in Massachusetts, like I said, we need a U value of 0.55 or an R value of 18.2, and that does not show up on that effective R value column there. So what do we do? And now you say to me, Rob, we had cavity insulation, or Rob, we got to take and get rid of that steel Z-girt and put a composite Z-girt in there. And you'd be right both times, and we'll get there. I'll show you that in a second. The last thing I'd like to say about this slide is that, metal Z-girts are basically verboten now. You can't, ASHRAE's definition of continuous insulation is continuous without thermal bridging except for fasteners and service openings. And so for years, people sort of ignored that it was a thermal bridge because you'll see in a second, if you stuff your cavity now with insulation, you can actually achieve that R18, but there's a caveat to that. So let us put some cavity insulation, some bad insulation in our cavity, and let's keep ignoring the fact that the metal Z-girt creates thermal bridging. And now, when we do that, and we look at our effective R values, we can see that very nicely now. If we use R15 on the exterior and R13 bat, we can get an effective R value of 18.5. Oh, we've complied with energy code. That's the problem with this scenario is that once again, according to ASHRAE, you're not allowed to use metal Z-girts because they are thermal bridges. And B, the moral of this story is that just because you've solved the thermal answer, it doesn't mean you've solved any potential condensation risk or moisture risk. And so that is why, thermodynamics and hydrothermal analysis is important, right? Because where those steel Z-girts get attached back to those steel studs, there is still thermal bridging, and it is possible that at certain times of the year in cold climate zones 5 and higher, you could create potential condensation risk in your wall assembly. And so that is why we have to take it one step further than U value, okay? So the other thing I want to say about this slide is that when we start to add that in our cavity, right? Even though building science says don't do that, keep it outside. You can use insulation inside, but you have to be cognizant of the fact that you use the right ratio of interior to exterior insulation. And the reason for that, again, is because you don't want that critical plane, again, that surface to fall below the dew point temperature. You've got to keep that warm enough in your scenario, in your climate zone, so that, let's say, should there be an air leak, right, in between the studs, let's say there's exfiltration, and that air, that nice warm air, comes out and starts talking to that jip board where the hole is, where the guy missed with the screw gun, right? We don't want that. It's okay to have an air leak, not really, because it's not energy efficient, but it's okay as long as you have the right insulation ratio there, so that you're not going to create potential condensation and moisture. So that's only valid, that ratio, right? That's only valid in between the studs, right? What they call center of bay, right? Where there's no thermal bridging. But where those girts or where this aluminum clip or whatever cladding attachment you're using, where that ties back to the stud, you got to take a further look. right? You got to do a hydrothermal analysis or a WFI analysis and figure out whether you're going to have potential problems here. When we talk about that insulation ratio, here's an example of IECC's table. It's climate zone 5, and our metal framed wall, the 2018, 21, and 24 obvious, the different revisions of the energy code, right? And we started out in climate zone 5 by saying we wanted R13 plus 7.5. Now, what's the reason for that, right? How do they come up with these numbers, right? One reason is energy efficiency, of course. You'll notice that the CI number keeps going up because we want to keep building more energy efficient buildings. And by adding thermal resistance, that helps, right? But why this particular ratio? Well, you'll find out that in general, and as a rule of thumb, the cavity insulation to the exterior insulation should be about 1/3 outside, 2/3, just as a rule of thumb to get you started. When you start to deviate from that, you most certainly should do a hydrothermal analysis, right? You want to make sure that you're not going to have potential condensation or moisture risk in your wall cavity. And so if you look at these different versions of the International Energy Conservation Code, you'll see 13 plus 7.5. That's a total of 20.5. If you took a third of that, I think it ends up being 6.7 or something like that. So that, to me, that's the third, right? That's the minimum R value you need on the outside of that sheet. And so if we have 7.5, we're fine because that's larger than 6.7. And if you do that for the other scenarios, you find the same thing. Notice in 2024, we're now given 3 choices, right? So all 3 options will work. You do no cavity insulation, and 15.2 is your CI, or you can do 13 plus 10, or even 20 plus 9 will work. Again, remember, these are all going to get affected or derated by studs and other thermal bridging anomalies on the outside of the building, okay? But that's where these ratios come from. That's why these numbers are what they are, and that's why they vary from climate zone to climate zone. So if we go back to our wall here again, right, that ratio, again, was meant for this center of bay area of the wall, right? Once you start introducing the thermal bridging, that's it. All bets are off. You've now got to address the thermal bridge, all right? All right, so now let's look at another example of thermal bridging. So now we have our clear field wall, and now we've added a parapet, right? A nice little cooling fin to the top of our wall that's exposed on 3 sides to the elements outside. And what happens then? Well, if we look at our resultant data in the chart here, in the pie chart below, we now see that we've reduced the R value of our wall assembly by over 55%. So the girts and the parapet now working together to derate the wall further. This is our beam, right? Our canopy balcony beam. And again, the thought process, and rightfully so, because we're all human, hey, that I-beam, that doesn't have a huge cross-sectional area. How much heat could it possibly draw out of the building? Well, we start to now see why it's important to address thermal bridging. In this model, I've used R15 as my CI. If you look up top here, I expect 29.3 as my nominal. I get 18.6 because of the Z-girts. It's reduced a little further due to the slab interface here. But then finally, when we throw the beam into the equation, look at that. We're all the way down to R6.9. Let's call it R7. That's R7 from R30, okay? So now we're over 75% of our nominal R value in our wall because we have Z-girts, because we have beams. If we threw a parapet on here too, now we're really in trouble, right? Excuse me again. One of the largest offenders actually is what I alluded to earlier, right? The position of the window in the rough open. And in this particular case, we've got our same wall assembly, our same clear field wall assembly. All we've done is pop a window in there. And due to the position of the window in the opening, the effective R value of the wall has now dropped down to 5.8. Okay. So we're going even further now. Now we're almost close to 80% derated in our wall assembly. And so this just gives you an appreciation or an idea of how thermal bridging can affect, your wall and roof assemblies. I think this is the last example. So this is obviously a relief angle, right? Traditional brick veneer cavity wall, extremely popular up here in the Northeast. It's aesthetically pleasing. It goes back to colonial times, uh, or even further back than that. So lots of schools, libraries, right, museums, and that's all great and well and good. But in today's world, where here in Massachusetts and in other locations in the country, our energy code is now a stretch code in certain locations and is very strict on thermal bridging, derating, and air leakage. Um, it's getting more difficult to build this type of wall system. It's getting very expensive to build this type of wall system as well, right? Because when you look at it as is, brick ties, and there's lots of different types, I know, can reduce the nominal R value by up to 30% of this wall, right? And then you throw a relief angle or a shelf angle in there, and now it approaches 70%. Okay. And yes, they do make thermally broken brick ties. Those are still going to be responsible for at least 15% as a D rate of your nominal insulation. And yes, you can take the shelf angles and put them on knife plates. There are some proprietary, manufacturers that make angles with brackets. Of course, the intent there is to reduce the surface contact area of the back spline of that angle up against the structure, right? You want to now use discrete points instead of this linear thermal bridge all the way around your building. But many times, those bracket systems still need some kind of thermal break behind them in order to comply with some of these emerging energy codes. Okay. Um, if you try to overcome the relief angle by adding more and more CI, like you saw in the GERD example, it's not going to work. Okay. You will end up with a wall 14 inches thick, which of course is not really feasible. It's very costly. So, but again, there are ways to do it, right? You use thermal breaks, you use mineral wool, you use thermally broken brick ties, and there are ways to get there. And it also depends on your energy code and what it says about U value, R value compliance. There are some trade-off methods that are available. It's just getting more involved. And I do have empathy for architects and building design professionals because there's a lot to keep track of now. And this ends up changing, to some extent, how you design your wall and roof assemblies. All right, so we looked at where it happens in an enclosure, why it happens in an enclosure. We took a look at some examples. Okay. Now, what do we do about it? Right? How do we reduce that transmittance or that heat flow and comply with energy code? And the answer is thermal breaks. Right? This is the classic example of a composite material being used as a thermal break in a bolted steel connector. Thermal breaks are, I alluded to trade-offs before. Thermal break, materials and solutions are the ultimate example of design trade because they must be strong enough to not interfere with the structural integrity of the connection, while at the same time, the whole purpose is to have a much, much, much lower conductivity, right, than the material that you're breaking. So you can't use cavity insulation in between two end plates, in a bolted steel connection. It's got a great R value, but it's nowhere near strong enough, right? So you got to find the appropriate materials. One of the things that I want to address today as a supplier of thermal breaks is going back to my thermodynamics back. This is an example. I picked it up. It says from the Scottish Energy Systems. What we have here is a piece of thermal break material here, right? It's got one temperature on one side, one temperature on another. It's got a thickness of X. Here is the equation for heat flow. Don't worry, there's no quiz. But the heat flow is a function of K, which is the thermal conductivity of the material, A, which is the area, the change in temperature, and the thickness. And here we have two examples, one column here, one column here. The temperature difference is the same from one side of the material to the other in both examples. The thickness is the same. Thermal conductivity, we have one that's got a conductivity 4 times higher than the other. The area, so when we do the heat flow calculation, it's no surprise that the material that's got a conductivity 4 times higher than the other has a heat flow 4 times higher than the other. Okay. But what happens if we change the thickness? What happens if we cut it in half? Is the heat flow going to go up or is the heat flow going to go down? The heat flow is going to go up. Okay. So there is a direct relationship between thickness and conductance of a material and heat flow. Okay. So those two variables are related, right? Now, what happens if we change the change in temperature from one side to the other? We cut that in half. Is the heat flow going to go up or down? And you find out that as you, oh, whoops, a little snag there. Did it work? Sorry, I'm jumping around. I can't see let me just move that. Okay. Sorry, I couldn't see that. So if we cut the temperature difference in half, no surprise, there's a relationship there as well to the heat flow, and the heat flow gets cut in half. Okay. So I just want you to be aware when you're designing connections and asking for a thermal break, um, the materials, the composite materials that are being used as breaks for these moment connections, um, do their physical properties vary? Sure. They're not all identical, right? Um, some have a conductivity of 0.5, 0.6, some closer to 0.8. Um, the thing about it is it's about thickness, right? Because they're all pretty much the same. They're not going to move the needle on the results of a whole wall assembly too much. But their thickness matters. So the thickness that you choose matters because you can't do anything about the conductivity values of these materials. They're set. Um, and until someone comes out with a material that's strong enough for a bolted steel connection, that's got a much lower thermal conductivity or conductance, then we have what we have. And so I'm just saying to you, be careful, right? Be cognizant of, I see details and all the time where, don't forget now, in a steel beam, right? We're breaking that beam. That beam has a very small surface area. Once we cut it and we add two end plates to either side, we've now increased contact surface area of that connection by whatever. Let's just call it 100. And so area is part of this equation, see? So now, whatever we put in between there, we gotta be sure of what we're doing and that the heat flow is calculated properly. All right. So that was just one thing I wanted to point out. We're talking about thermal breaks now. We're talking about how to solve the problem. Okay, so let's look at our traditional cavity wall again. Um, we're only going to put the insulation on the outside. It's best for building science. It's the best way to keep that critical plane warm. And we can do that now because we're using a composite Z-girt rather than a metal Z-girt, right? Because we can't use the metal Z-girt anyway, because it's going to cause us moisture problems potentially in cold weather climates. And so now we can see if we look at our resultant R values here, that we can now comply with zones 5, 6, 7 by using R15, R20, for example, for our CI. Now, one caveat, right? The definition of continuous insulation, as far as ASHRAE is concerned, says continuous without interruptions, right? Well, composite Zs and other thermally broken cladding attachment systems still interrupt the insulation, so it isn't truly continuous technically, is it? But these composite Z-girts and other proprietary thermally broken systems do simulate as close as possible continuous insulation, right? Because as we saw in the previous example, they pretty much now, if you look at here, we expected, for example, if we used R25 for our CI, we expected R28.3. We're actually getting R27. So we are almost nearly close to 100% efficient now with our exterior nominal R value, right? And so we are doing the best job we can now of simulating truly continuous insulation when we have to use a cladding attachment system, right? You don't have a cladding attachment system. If you're using an EIFS type of system or something like that, you don't have to worry about this. Here's our parapet, right? We're going to come back to our parapet, and now we're going to put a thermal break underneath the parapet, right? To try and help with that heat loss, that transmittance up top. And when we do that, we do actually increase our R value, our effective R value by about 9%, right? And so just using a 2-inch thick piece of thermal break material that's got an R value of 3 per inch, we're able to do that. But keep in mind too, when you're looking at all the different thermal bridging anomalies in your enclosure, right? There are going to be some that are much more offensive than others or larger than others. And there's sort of going to have to be a cost trade-off or a what's really important to address discussion. Um, Here, we still have the steel Z-girts in the wall. We get rid of those. This R value here of R14 is going to increase, obviously. So maybe we treat the parapet, maybe we don't. What I would say to you about parapets is there are other ways to sort of accomplish this. Some people like to wrap the parapet with insulation. That's great. That's fine. That will keep the heat in, of course, but just keep in mind that this indoor space, conditioned space, and this parapet cavity are two different climate zones, if you will. Okay. And even though you wrap it and get your U value, be careful that the conditioned air, if there's an air leak, is not going to start talking to that unconditioned air up in the parapet cavity, where you will now have some potential dew point issues. Okay. When you use a brake, you are actually, again, coming as close as you can to CI, or continuous insulation, and then you don't have or shouldn't have the concern of moisture in the cavity there. All right, here's our beam. With our beam, I took a piece of 2-inch thick thermal brake material. It had an R value of 0.7 per inch. And so you can see in the chart here, I've run through a range of R values of material. Right? And so if we're 2-inch and we're 0.7 per inch is an R value, then our R value is basically 1.5, technically 1.4. Don't tell anybody. And so when we run the model, we get another effective R value answer. And the answer here is 9.2. If you remember from the first beam model, without a brake, the R value of the wall was 6.9, okay? And so with a 2-inch brake, right, we've got it up to 9.2. That's about an R 2.2 increase. That is how offensive or how large the thermal bridge is in a beam connection like this. 2-inch thick now. You've lengthened the grip of the bolt. Structural engineers, I don't blame them. Probably not real comfortable going much thicker. We've done some 3-inch breaks. But if you get thicker than that, you start to be concerned about structural integrity, right? And so getting the wall up to R9 with the beam brake is good. There's one other thing that's better than that, but this is we're on our way, right? Because we're also going to address the steel Z-girts, and that's going to increase the R value as well. Don't forget, in climate zone 5, you've got to get all the way up to R18. Here, I'm going back to our discussion on conductance and thickness. And if we took the same range of R values of material, but we made that thermal break now from 2 inches to 1/4 inch, if we only made it a 1/4 inch thick, our R value would be what's shown in red, okay? And then when we look at our effective R value column of our wall assembly, can anybody spot the problem? Problem is that the answer now, no matter how we slice it, no matter what the R value of the thermal break is, the R value of the wall is now 6, right? Problem with that is when we started without a thermal break, the R value of the wall was 6.8, right? And so we've really gone backwards, okay? We have made a physical break in this beam, but we have made the heat loss worse. We've actually made the conductance worse because the thermal break's too thin, right? Given the area of the beam, the area of the end plates, this particular example, this does not work, okay? And so it's just, again, my experience and my advice, just be careful when you're designing thermal breaks of what we're actually trying to achieve. I know for a fact, none of us are trying to go backwards, right? Okay. Now, I mentioned there was one other way with bolted steel connections to use a thermal break. And there are these other, so these aren't materials. These are what are referred to as manufactured structural thermal break assemblies, okay? And they are basically stainless steel, hollow steel tubing and plate, and stainless steel bolts. And then they are encased in some form of insulation. And here I've used our same wall assembly, and I've done some thermal analysis, thermal modeling. And here in this scenario 1A, we now have an effective R value of, let's say, 12, okay? And that is using still the steel Z-girts. If we use the composite Z-Gerts, that is scenario 2A, we can increase the R value up to 14.8, right? Great. A little bit better than using a material, but still not good enough for energy curve, right? We got to somehow, in zone 5 again, get to 18. So if we now increase the R value of the CI from 15 to 25, which is this scenario 2B, and we use the composite Z-Gerts, we now have an effective R value of 18.9, okay? But R25, keep in mind, that's 4 inches of polyiso and 6 inches of mineral, right? So walls get thicker, the thermal break gets wider. These units are a little over 3 inches thick, right? So it's just another way, though, to achieve compliance. All right. I have talked about several times keeping the material surfaces above the dew point, right? If we look at our beam model and we take a cross section of it, and I apply winter conditions in Chicago, for example, and then if I remove all the temperatures that are above the dew point, let's look what happens in this top cross section here. All the temperatures above the dew point are removed, so only the temperatures below are here. And what happens? This black line, that's our dense glass. That's our critical plane. That's our AWB. And we now have temperatures left over that are behind that, okay? And so what that means, it doesn't automatically mean that we have bulk water in our wall, but what it means is that we have potential for condensation risk, okay? This is just a quick and dirty way to do this in a thermal model. What you need to do next is a hydrothermal model to actually confirm that you might have water or condensation problems. If we then install the thermal break in the beam, though, this is the image below, what happens? You can see nicely that all these therms, right, all these patterns have been pushed out, right? So we've pushed the dew point line out into the insulation where we want it, away from our sheathing and our AWB. And that all works very nicely except for one area. And that is, in the model, we still have steel Z-Gerts. And you can see where behind the steel Z-Gerts, we have some temperatures below the dew point that are behind our sheathing, okay? Once again, making the point, you cannot use steel Z-Gerts or aluminum clips or metallic cladding attachments because even if you can beat the thermal game, you're not going to beat the potential moisture condensation game, okay? Down in Houston, it's just the opposite math. We're trying to keep the warm, muggy air outside from getting in contact with the cooler air inside, right? And so it's not intuitive to think that thermal breaks could be used in warm climates. They're for cold climates, right? But something needs to be done in the warmer climate zones as far as keeping the surface temperatures of the materials in our assemblies above the dew point, right? Okay. One more example here. This is our beam. I took a look at 3 locations in this model. The first location, temperature 1, that is the sheathing temperature directly behind a Z-Gert. Temperature 2 is the sheathing temperature, but in between the studs where there is no Z-Gert. And temperature 3 is on the warm end plate or the inside end plate of the break on that inside surface, okay? And let's see what we found out. So these are your 3 locations here, 1, 2, 3. Scenario 1A is a metal Z-Gert. And so the temperature at that surface behind the metal Z-Gert, 21.9. The temperature of the sheathing where there is no Z-Gert, close to 51. And the temperature just behind the thermal break, 62. If we change to composite Z-Gerts in the green, we do a nice job of increasing that temperature by about 20 degrees. That's a big swing, right? Here in the yellow, when the surface temperature is close to 22. So, okay, again, with the metal Z-Gerts, the surface temperature was about 22. And yes, we do have a potential for condensation risk here. But when we go to the composite Z-girts, no, we do not. Okay. Um, and then if we use in scenario 3, right? In scenario 3, we're using not a physical thermal break. We're using a coating on the beam, right? There's a coating on the beam. And what that does, it helps keep the surface temperature warmer. And as you can see, the temperature in blue here, it's not as warm as the physical break, right? But there is no condensation risk, okay? So the coating does help prevent condensation risk and moisture. It's not as effective with conductive heat loss, but if they were used together, a physical break and the coating, that would be the best of both. All right, there is seriously only 2 more slides. I'm glad I was entertaining today, hopefully. If you're a passive house consultant or designer, or if you're working on a project that has passive house compliance requirements, passive house is a way to build that is all about occupant comfort and energy efficiency, right? And in a passive house build, they like to say thermal bridge free, meaning no thermal bridges, right? But what they are really saying is you're only allowed this as a maximum transmittance or heat flow with your thermal bridge. And here, if we take a look at all of our examples we looked at today, okay, these were the results, the heat flows with the point and the linear transmittances. And you can see by passive house standards, we are way off, right? We got a lot of work to do. We're 29 times over, 48 times over, 22 times over, right? And soon as local jurisdictions and energy codes adopt passive house levels of compliance, this is going to become a big deal. All right, wrapping up here. Preventing thermal bridging with thermal breaks. Structural integrity is of utmost importance, right? You can't afford to have any compression in any of these connections. If you do, it needs to be within tolerance. You got to be careful of long-term creep. Depends on the material and the application. Thermal conductivity. We spent some time on that, right? That's the whole point. We need materials that conduct heat 500, 400 times less than steel, concrete, aluminum. Fire resistance, sadly, not talked about a lot, at least with me. The Z-girts, the composite Z-girts, yes, those all have to pass an NFPA 285 test, which is a wall assembly fire test. But rarely do I get asked about the other materials. If you have one balcony or one canopy in your wall and it's 2 pieces of composite in the wall, maybe it's not a big deal. But if you have 100 balconies times 2, you have 200 pieces of composite in your wall. Technically, all these composites are combustible, just like aluminum. They have a very similar combustion temperature. But because they are thermally set composites, right, they don't burn, they don't melt or drip. Those are thermoplastics, not thermal sets. But they do have, properties that need to be looked at as far as the building code official, and are they going to be an issue or not, right? So we have to think about those 3 things when we think about thermal breaks. And I do apologize. I have never had that problem in my life with the slides. Hopefully you found some comedy in it. I don't know, but there you go. So there's my presentation on thermal bridging. A little bit different than some of the others, but I do appreciate your time today. I know that your time is valuable, and an hour of your time is precious, and I appreciate it. And thank you also to Acelab for hosting this.
Thank you, Rob, so much. Any questions and all of that stuff you'll receive after today's presentation. So Rob will follow up with you guys directly. Thank you for a great presentation, and I hope everyone has a good rest of their week.
Great.
All
Thank
right.
you.
Bye.